Example 7, adiabatic mixing. Mixing is a very common process in industrial field. Two streams are mixed as the figure. One flow from the main tube flow. Another flow comes from another tube into the main tube. So two streams are mixed. We can use the energy balance equation and mass balance equation can do some analysis for the mixture process. In this process, no heat flow to or from the fluid. No work is done. Hence, M.1 times H1 and plus M2 times H2 equals M3 H3. Means the energy in the state 1, the energy together, certainly is the final state, state 3. For a perfect gas, we have H equals Cp times T. Cp is specific capacity. T is temperature. Hence, the equation we can change M1 point Cp1 times T1 and M2 times Cp2 T2 equals M2 Cp3 temperature 3. Here is the energy balance equation. If two streams are of the same flow with same specific heat capacity, Cp1, Cp2, Cp3 is same. So the energy balance becomes simple. M1 T1 plus M2 T2 equals M3 T3. But the mass balance equation, we know M1 plus M2 just is M3. So this equation is equals M1 plus M2 together times T3. This mixing process is highly irreversible due to the large amount of adding and the churning of the fluid that take place. Many mixed, many irreversibility. So here is certainly is a irreversible process. Okay. Last several pages, we discussed several examples. We can use the steady state fluid energy balance equation. From this page, we discuss non-steady flow process. Non-steady. In this picture, it is a non-steady flow system. The rate of mass flow across in the boundary of the system at inlet is not same as the rate of mass flow across in the boundary of the system output. Just to say, input the mass flow rate and out the mass flow rate is not same. So in this case, in the vessel, the mass may be increased, may be decreased. So the mass in the vessel is changing. So it is not a steady flow process. In this non-steady flow process, we can do some analysis from the energy balance equation, because energy always is balance, always is conservation. Let the total energy of the system within the boundary at any instant be E. During a small time, very short time interval, let the mass entering the system is delta M1, and mass leaving the system is delta M2. Let the work and heat input is delta W and delta Q. Just here is mass into and mass out. Some energy into. Maybe the system do some work for the people. So delta W and delta Q is not zero. It's not zero. Because we know goes into the mass is delta M1. Certainly M1 carried some energy, internal energy and flow work. So carried some enthalpy is H1. So at inlet, entering energy is H1 delta M1. At outlet, leaving energy is H2 delta M2. Here is the mass carried the energy. Certainly, this mass is still includes some kinetic energy and potential energy. So, from the first law, energy balance, but the mass carried energy entering the system is delta Q. Delta Q is outside give some energy into the system. Delta W is the system give outside the work plus delta M1 is goes into the mass. H1 is the enthalpy. C1 power second and Z1G is the kinetic energy and potential energy together. So this term is all of the energy goes into the system. The energy leaving the system is delta M2 times H2 and C2 power second divided 2 plus Z2G is all of the energy leaving the system. Here we applied the first law. We obtained delta Q plus delta W plus delta M1 H1 plus C1 power second over 2 plus Z1 G together minus ZM2 times H2 C2 power second and Z2G is potential energy and the enthalpy together is leaving the system. Into the system minus leaving the system, there is some difference is the delta E equals delta E. E is the energy storage in the system. Delta E means the storage energy in the system there is some change. Okay, during a finite time, very short time, from initial state to the final state, we can think there is one initial state, final state, process finished is the final state. The total work and heat goes into and goes out the work and thermal energy Q together is capital W and capital Q. The initial parameters I M prime, Z prime, U prime, small u prime. Final parameters I M2 primes, Z2 primes, and U2 primes is the final parameters. So together the storage energy change together. Just is M2 prime times U2 primes and Z2 primes and times G minus M prime times U prime and times G. Why there is no kinetic energy? Because we think we have a final state. Final state, just we open the valve. The final state, we close the valve. So there is no kinetic energy. Therefore, we obtained the final equation, capital Q plus W plus sigma delta M1 H1 and state 1 the kinetic energy and potential energy together minus M2 delta M2 times H2 plus C2 power second over 2 plus Z2 times G together. Here is all of the goes into the energy minus goes out the energy. Just is the storage, the energy in the system. So we obtain the very long the equations. Noticeable, sigma delta M1 minus sigma delta M2 just is the mass change. Just is the M2 primes minus M prime. Here is the energy balance and the mass balance. Last page, we obtained a very long energy and mass balance equation. These two equations is very important, but this equation may be complex, very difficult to use it. Now we give an example. First example is the filling process. Filling process, like this picture, just there is an input, no output, especially when the main pipeline, the parameters is constant, the problem become simple. For filling of a bottle from a source which is larger in comparison with the bottle. For example, here is a pipeline. Pipeline maybe is very big, the vessel. Here is a very small vessel. We can think the pipeline, the parameters is not change. In this case, the work, potential or kinetic energy do not require to be considered because only one input goes into, we can think is not so fast. So potential energy, kinetic energy can be ignored. Also, delta M2 is 0 because no output. So delta M2 is 0. For filling process, we have one equation, Q plus sigma delta M1 H1. H1 is enthalpy of the working fluid. The final state and initial state is fixed. So the energy difference is M2 primes times U2 primes minus M prime times U prime. Just to say, in the vessel, the energy change just is Q and sigma delta M1 times H1. If H1 is constant, can move to outside from the sigma. So sigma delta M1 just is M2 primes minus M1 is the mass change. Finally, we obtained Q is from outside goes into the system. Is total of the thermal energy goes into the system plus H1 times the mass change just is the energy change, energy in the bottle change is M2 primes times U2 primes minus M prime times U prime is the energy change. Another example is fluid escaping process. Escaping process just opposite from the filling process. Filling just is one input. Escaping process means only one output. There is no work done, and in this case, delta M1 is 0 because no input. So finally we obtained the energy balance equation. Q means all of the thermal energy goes into the system equals sigma delta M2 times H2 plus C2 power second divided 2 means the kinetic energy least escape. The kinetic escape plus m2 prime times u2 prime minus m prime times u prime means the bottle, the energy difference. In this case, because C2 maybe is changing, because the vessel with the process, maybe the pressure become decrease. So in this case, in the bottle, in the vessel, the pressure become decrease. So escaping speed may be changing. So C2 is very difficult to fix, to obtain. Just difficulty is that the state 2 of the mass leaving the vessel is changing. It's not constant. In this case, in this equation, sometimes it's difficult to solve. If tell you the C2 is very small, also or to say is very slow escaping. In this case, C2 power second becomes smaller, becomes 0. This equation becomes easy to be solved. Thank you.